The linear relationship, the homoscedasticity, normal distribution of residuals, and the independence, we've all talked about several times. I mentioned earlier that we're adding these no omitted variables in the variance of x greater than 0, which were implicit assumptions that we had talked about, but we're going to make them official here and talk about them more fully. What's interesting is there are a lot of tests for these assumptions, but what's kind of funny is they actually usually have their own assumptions, which you end up having this problem of we need to test the assumptions of our model, so we're using tests that also have assumptions that could be violated. And what we end up getting is this kind of Inception problem where we have a test, we have assumptions within assumption within assumption, and at some point it doesn't do us a whole lot of good. So what we often will use, we're actually going to rely on plots, and we've shown these before. We're going to talk about them more fully, but the reason why is they don't rely on any assumptions. We're just looking for patterns and trusting what the residuals are actually saying to us. All right, so as it comes to these two that we added, I just wanted to highlight a few things about them. First, the no omitted variable bias is largely theoretically based. It can show up as weird residuals, like maybe we're missing an effect like a quadratic effect. But remember that this is really based on theory. It's very difficult to go into a model and know if there's omitted variable bias just by looking at a model or looking at diagnostics. This is one reason why we have to go into regression, really thinking carefully about the causal mechanism. And we can use any of those causal frameworks that we talked about earlier in the class to decide what variables actually need to be in the model for this to be most valid. The other one, this one's actually really easy to test. So with the variance of x being greater than 0, we just need to say, are there at least two values in x? If there's only one, then we can't use it. If there's at least two, then it's something that we could use in the model. When it comes to the linear relationship, if we're looking at the raw data like we are in A, we're looking at x and y. If we try to fit just a regular regression, it's going to be that straight line. And you can see already that that line does not represent that data well at all. In fact, it's actually this curved relationship that represent the data really well. Now, if we were to run a regression without knowing that about the data, what we could get out is actually this B plot, where we're looking at the residuals and how they relate to X. So these are, the line right there, the dotted line is like the predicted line, and then the y-axis is telling us how far away from the line each of the points are. And if you got a scatter plot that looks something like this, you already know, okay, that doesn't look normal. I see a very clear pattern where it's definitely not a cloud. And here I write that they are T residuals. I say T residuals, that is just essentially a standardized form of the residuals. So it's kind of like a z-score where this, on the left-hand side of the B plot, you're seeing values that are really low, like -3. So that's kind of far from the line, but nothing that we wouldn't expect, at least sometimes. And we see a really high value towards the middle, which is like 2.5. Again, nothing too crazy on how far away they are from the line. But what we're looking at is the pattern. And this does not look like a random cloud of points. Now, if we actually run a nonlinear model, which we'll talk about in the next unit, we use a polynomial regression, the residuals from that model is shown in C. So when we actually account for this other effect, this nonlinear effect, the residuals start to look good. So sometimes when the linear relationship seems to be failing, that's just because we have omitted a quadratic effect. So you can see that the assumptions actually go together a little bit. If one is problematic, it can make the other one problematic as well. So it's good to see here that the residuals were not good until we added the quadratic effect, which is due to this omitted variable bias. So if you see something this stark, it definitely means that there's a quadratic effect going on. One of the issues, though, is that it's usually not this strong of an effect. You usually don't see it this clearly. And so often, the linear relationship is also theoretical. You can check the residuals. That'll tell you if there's a big deviation from it. But when that's not super clear, again, you're relying on theory. Should this have a roughly linear relationship, or should it curve? Another one is the homoscedasticity of residuals. And this one is just saying that the points are this nice random cloud around the line, that the variance around the line does not change systematically across the line. So what we're seeing in plot A is a nice homoscedastic plot of residuals. Just looks like a random cloud. The variance doesn't look like it's meaningfully changing across the line. It may look a little bit smaller on the edges, but that's okay. It's just because extreme cases are supposed to happen less often, so it's okay that it looks kind of like a football shape. That is totally expected. When it comes to B, we're actually starting to see one example of heteroscedasticity. And this is where the variance around the line on the left-hand side is really small and gets bigger and bigger and bigger as it goes towards the right side. This often is called fanning out. It's fanning out. This can happen in the other direction too, where it's really small on the right side and gets really big as you go to the left side. C is this bow tie look, and it's where the variance is really big on the outsides and gets really small as you go towards the center. That's also heteroscedastic. And then D is a form of heteroscedasticity I've never come in contact with in real life, but it's kind of this diamond shape where it's really small on the outsides and starkly gets really big in the middle. That can be problematic too. What all this is trying to show are different ways that the residuals can show problems with this assumption of homoscedasticity. Again, we're looking for something like A, something that looks like a random cloud. The normally distributed residuals with a mean of 0, this one is somewhat tricky by just eyeballing it. We actually have a special way that we're going to look at it in just a sec. But the idea is that the residuals at each point of x are normally distributed around the line. So if I go to x equals 0, the points should be roughly normally distributed according to y. One way to think about this is, are more points closer to the line than far away? Because that's what we would expect with a normal distribution, is that more points are closer to the middle than there are far away. But this is really hard to visualize just by looking at a scatter plot. So the best way to actually look at this one is with what's called a normal QQ plot, or a QQ plot. What we're looking for here is that the dots are along this diagonal line. If they're pretty close to the line, that suggests the points are roughly where we would expect them to be if we assume normality across the whole line. What's awesome is this is one of those plots that just gets outputted pretty automatically in R. Another assumption is the independence of residuals. Again, this one is generally theoretical in nature. You need to ask yourself, are the observations or participants independent? Or are they connected in some way? Time series almost always violate this assumption because previous time points are correlated with the current ones. So longitudinal data, time series, anything like that where time is involved, you generally have a violation of the independence of residuals. So in many cases, what we'll actually use is multi-level modeling. And there is a class on that here taught in the psych department here. You can take that course, and it really is just an extension of what we learn in this class about regression. It just extends it to a situation where the observations are connected because there's repeated measures or there's clustering within classes where students are influencing each other or the teacher's influencing all of them. So this one, again, is very theoretical in nature often. There are tests for this as well if you're really concerned about it. We're not going to talk about any of those right now, but if you're concerned, but you don't have a really good theoretical reason why, you can either use multi-level modeling and adjust for it, or you can test it. All right, so one question is, what if I find problems in my data? And I'll tell you right now, you're going to eventually. There's rarely the case where your data, the whole data set is just perfect. There's no problems at all. So I'm going to give you just a few ways that you can correct or deal with the irregularities. One of those is called correction. This is just go in and correct the error that led to the extreme value. Sometimes an extreme point is extreme just because we put in the data wrong or in some way it is not actually measured correctly. When that's the case, we simply just fix the error. When that's not the case, sometimes what we can use is a transformation. This is where we transform the outcome or predictors using what's called a monotonic transformation. These are transformations that do not change the order of the variables. So if I'm lower at a lower point than you are, a monotonic transformation will change the distance we are from each other, but will not change the order. I will not leapfrog you or vice versa. Examples of these are log, square root, square. All of those are monotonic transformations that sometimes can make really extreme values come in. For example, log transformation brings really high values and it brings it in so it's not so crazy high compared to the others. Another one is elimination, and this is where you remove the extreme value. Generally, I recommend if you do this to report the results both with and without the extreme value in any publication, at least as supplementary material. The reason why I recommend that is it gets really easy to start eliminating points that are inconvenient, that maybe are kind of robbing you of some significance. When that happens, it gets very dangerous to be scientific fraud. So if you're going to eliminate a point, you want to be very transparent about it. And that includes saying that you did it, but it also includes showing what the results would have been if you had left those points in. There are cases where it's just accepted to remove some cases. For example, if there's a problem with they just didn't answer it in a way that could be possible, removing the point may be the only way to really analyze the data. And that is acceptable, but you still want to show what you did, even if it's not possible to show what the results are with that point. Generally, showing the results with the point and without are when it's a little bit more ambiguous about is that point indeed wrong or not. It just seems like maybe it is. So if you remove it, you need to show the results both ways. Another approach is robustification. This is an approach that makes your results less sensitive to the extreme value. There's lots of ways to do this. We're going to just briefly introduce three that help you deal with it in terms of the standard error. But there are ways of dealing with it in terms of the actual estimate itself as well. And then I bring this one up We're going to talk about this in Unit 4, but there are ways of dealing with really strange distributions of outcomes. And it's a whole family of methods. It's called generalized linear models. And these can handle categorical, ordinal, or otherwise strange outcomes, even binary outcomes, so an outcome with just yes, no. We're going to talk about especially logistic regression and a few others that actually are designed to handle those cases. Sometimes general linear models or generalized linear models don't work fantastically for a given situation, but sometimes they are perfectly designed for it. So we'll get you introduced to those so you can know when it might be useful. So before we talk about these specific approaches, I want you to consider this example. So let's say our friend, the child language researcher, now wants to see if story length, the outcome, can be predicted by narrative quality, the predictor. This time they decide to use sentence count as a measure of length, because why not? And so we run the model, we have sentence count as the outcome and story grammar as the predictor. And we get this result. We have the estimate is 0.95 and it's highly significant, suggesting there's probably an effect out there. This is a significant effect. And for every 1 unit increase in story grammar, there's a 0.95 increase in the sentence count. So naturally, if you're in this situation, you're like, wow, that p-value is essentially zero. It's super close to zero. It's very significant. This effect is meaningful. But before we get too excited, let's check the residuals. So we print out the 4 plots, and we're starting to see maybe some problematic patterns. So this first one, the residuals versus fitted, we don't have a huge issue with linearity per se. The line is fairly straight, but we're starting to get some hints of maybe some problems with homoscedasticity. If we go to the plot below, the scale location, it further shows that we do have a problem with homoscedasticity being violated. So we have this heteroscedasticity, where on the left side we have pretty low variability, and it gets really big in the middle, and then goes down just a little bit towards the end. So we're starting to get that diamond shape, or yeah, really the diamond is probably the best fitting for here. So we may have a problem with that. We also look at the normal QQ plot, and we can see that the points really don't seem to follow the line very well. And we have several on the right-hand side that are really high up, really far away from the line. So it doesn't look like we have a normal distribution. And possibly, when it comes to the residuals versus leverage, we have leverage across the bottom, we have the residuals across the y, and then Cook's distance is actually measured on there. It doesn't show it because there's nothing that's really high influence in this data set. But we're starting to see some that have big residuals like 301. And we're also seeing some that have big, higher leverage compared to the others, those that are kind of far out on the right-hand side. When it comes to Cook's distance, though, the influence, we're not seeing any that are really, really problematic there. What would happen with those is that they would be really far into the right-hand upper corner or right-hand lower corner. One thing that we could try is doing a log transformation in this case. We have some experience with this data, and maybe we've seen log transformations have worked. So let's try it. And so we use a log transformation of the sentence count, still predicted by story grammar. And now our estimate changes. It's now 0.097. We should expect it to change because we've made a transformation on our outcome. It's still really significant though. When we get to the nonlinear models, we'll talk more fully about what that estimate means. But I'll give you a hint right now. When you do a log transformation of the outcome, the way that you interpret the predictor would be for a 1 unit increase in story grammar, there's a 9.7% increase in sentence count. So it's now in percentage units. It's an approximation. We're going to talk about that a lot more. So now let's check our residuals. All right, so the first one, the residuals versus fitted, that one's already looking better. It looks a little bit more like a cloud than I did before, still looking very linear. We look at the plot below it, the scale location. That one looks a ton better. We have a lot more of a cloud than we did before, and the line is roughly straight. And our normality is definitely far better. Those points are very close to the line. And when it comes to the residuals versus leverage, we still have some points that we want to look at because they have either a high residual or possibly high leverage. We just want to make sure that those points look valid. But I don't see any from that plot that tell me that there's anything really problematic. Most of the points are fairly close to each other, which is often what you're looking for in a plot like that. So before we move on, I just want to say this is going to take some practice. It's okay if you don't understand what's going on right away. Often I think the normal QQ plot is fairly easy to start to look at. You're like, oh yeah, the points are pretty close to the line. But the other ones may be more difficult to understand what pattern we're looking for. Give it time, practice with it. Every time you run a regression, check the residuals, and you'll start to get a feel for when things look weird and when things look normal. And of course, reach out with questions. Now note, going back to the example, we want to say, in this case, a log transformation worked pretty well in addressing the violated assumptions. It's not always going to work just like that, one try. Sometimes it's going to take some trying to see, some trial and error. But depend on the data, it may require more data manipulation or alternative methods like robustification or generalized linear models. But what we're hoping is that this highlighted the importance of plotting your residuals and never assuming your data is just good to go. Even when the results are really exciting, like, oh, we're finding something significant, it looks like something's happening, it's really dangerous to just jump in, especially as you're starting to report this. If you start to report it and then you find out there's violations and then you have to make changes and it changes the results, for one thing, it makes the results feel more iffy, but it also can be embarrassing as a researcher to be like, well, I forgot to actually look into the assumptions. Everything was wrong about what I told you before. It's not shameful, I will tell you that. Everyone does it. At some point, you're going to forget to check the assumptions. But the less often you do that, the less problems you're going to run into, and the fewer times you're actually going to be embarrassed by not checking that. All right, really quick introduction to robustification techniques. There's really two main ways of robustifying. One is use an alternative way of estimating the coefficients. There's like generalized least squares and a bunch of others that adjust how the estimates are calculated and weights them. So extreme values don't impact the results as much. If we have time, I'm going to try to have an example of one of those in the in-class example, but there's no guarantee on that. The other one I wanted to show is you can use an alternative way of estimating the standard error, or more generally speaking, the uncertainty. And this is the one we'll talk about it a little bit more right now. When it comes to this sort of robustification, we have heteroscedasticity, consistent standard errors. we have bootstrapping, and we have permutation. The heteroscedasticity consistent standard errors uses an equation to make the standard errors consistent. So as the sample size increases, the standard error is closer and closer to the true value. It uses often what's called the sandwich estimators. It's kind of this iterative approach to finding the most accurate standard error when you have heteroscedasticity happening. And there are many versions of this. HC3 and HC4 are the best. Those are just the names of two of them. And there's definitely ways we can do this in R. We'll show a few of those. There's also bootstrapping. This one is really cool. This one you can use at any point. It just resamples from your sample with replacement. So it takes one of your data points and is going to use it, and then it puts it back in. So it could draw the same person multiple times. And what's interesting, when you actually do this and you do it many times, you actually can get SEs, confidence intervals, and p-values without relying on statistical theory, which means you don't have to rely on the standard errors that you would normally get. So bootstrapping actually empirically estimates your standard error and your confidence interval and your p-values. And it works with any statistic. So we can use it with regression with our coefficients, or we can use it with a mean value if we're trying to estimate that in a population. It works in a lot of situations. It's a really cool approach. Then the last one, the permutation, it randomly shuffles the data and reruns the model many times to find essentially what the null situation would look like. So if we actually were living in a world where there was no effect, permutation would show us what that world would look like, what kind of results we potentially could get in that world. And then we compare our real result to that world and see if it lines up very much. And again, it works with any statistic. So heteroscedasticity consistent standard errors, very specific to regression. But bootstrapping and permutation work really across the board, and they're really cool approaches. They used to be a lot harder to do, but with computers getting more and more powerful, it doesn't take a whole lot of time to do. One note is that you can use any of these whether or not homoscedasticity exists. You'll actually see some papers use one or more of these no matter what. They don't even really look at, do we have problems with heteroscedasticity? They'll just use one of these approaches anyway. And a reminder, no model is correct, but some models are useful. Everything that we talked about today is we're trying to make our model most valid, most useful. It's never going to be perfect. It's never going to tell us the exact truth. It's really important that you know that when it comes to interpreting, but it's not an excuse to not go through the effort, make sure that the model isn't violating any assumptions and that you don't have any influential or extreme cases. So again, no model is correct, but some models are useful. If you want your model to be useful, you need to check the diagnostics and look through your data to understand them better. So lastly, these are the resources to check out. We got a blog post explaining bootstrapping versus permutation testing, if you're interested in either of those. We also have another one about outliers versus high leverage observations. And there's one that talks about data transformations in R and when to use them. Again, we're going to talk about transformations a little bit more in nonlinear modeling in Unit 3, but it's great to dive into it now. It'll make it easier to understand it when we get to it. And of course, assumptions and a beautiful picture of red rock. If you have any questions about anything we've gone over today, please reach out. These are very important topics, and they're very important that you get practice with them so you can see when problems arise. In our in-class example, we're going to show how to use the diagnostics with a bigger sample size than 12, which will be useful in more of your situations where you're actually using data. Um, and again, please reach out if you have any questions about those or about how to deal with problems that you do find when you run the diagnostics.